Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe how to write equations for what's called an oblique impact. So what we're looking at, I've got this red mass here and this green mass here, and I've already kind of attached variables to these masses. As a rule of thumb, I always use letters to represent different masses and numbers to represent different time frames here. So this mass to the right is the one I'm calling mass A. This one right here, and this animal right here is the one I'm going to call mass B for the remainder of this video here. So what we're looking at here is a snapshot in time before these things collide, and then VA1 is the velocity vector of mass A, picture 1, VB1 velocity mass B, picture 1. All right, second picture, this is after they collided now. Now what's going to happen is these things will likely change in both speed and direction. So VA2 is the new velocity vector for mass A. VB2 here is the new velocity vector for mass B. Now, I haven't put any angles in yet because I want to spend some time talking about one, all the different directions that it's possible to write equations in. And this picture that I've labeled 1 to 2, this is the actual time here where the masses are in contact with one another. So the contact might look something like this. Now, it's really important when studying momentum to very clearly understand how the contact occurs. So this surface in contact has two types of forces that we could consider. There could be a normal force between them and perhaps even a frictional force between them. You might get a frictional force if, say, one of these were spinning during the impact. For the rest of this video, I'm going to assume the frictional force between them is small to 0 and we only have normal forces between these two. Now, I'm going to go ahead and draw these force vectors on these particles. So, if there is only a normal force between these, then that normal must align on this axis here. A moment to get that looking about right. And I'm going to go ahead and draw two of them because there's a normal on mass B, the green mass. There's also a normal on the red mass. So if I were to draw the normal force on this green particle, that force would be this way. And I'm going to go ahead and actually make it an impulse by multiplying by time. Now, the way I've written this is a normal force, this is a delta t, so this is now an impulse. This normal now would be an average normal force over the time interval. If I were to write this in the language of calculus, this would actually equal the integral of n dt, where n is actually a time-dependent force during the impact time. But I'm just going to write n delta t for this video. That's good enough. All right. By Newton's third law, this normal, which is down and right on mass B, that normal acts in this direction on mass A. So there's the two normal forces. Now, again, Newton's third law, forces always appear in pairs, equal in magnitude, opposite in direction. So there's my two normal forces. I probably should even go back and shorten this one up a little bit here, because if they're equal in magnitude, they should be the same length in the picture. Oops. And again, all I've done is tacked a delta t onto these to make these impulses. The reason for doing that is because when you're talking in terms of when you're talking in terms of momentum, which is the number one concept to apply to impacts, impulse is the quantity that changes that. Now, I'm going to start by talking about the momentum equations. There's really all kinds of momentum equations we can write for this system. And let me back up and even talk about the word system. We can define a system in a lot of different ways. So let's imagine for just a moment we define this as our system. Clearly there is a change in momentum. I mean, VB1 is up and right, VB2 is down and right. That change in momentum is occurring because of this impulsive force right here. we could define this as our system, and again I would say clearly there is a change in momentum because again this velocity vector and hence the momentum vector is down and right, and now it's up and right. So if we define our system as these individual parts to it, there are changes in momentum, or at least for the most part there are changes in momentum. However, there are directions where momentum is conserved even individually. So what I'm going to do right now is draw in a coordinate system that I'm just going to call a potential coordinate system for this problem. If I draw a coordinate system, and I'm going to put it right here in this picture because I think right here is where it'll probably make the most sense. I'm going to put a little coordinate system right here. And I'm going to align this coordinate system in such a way that this axis is parallel to the normal. So I'm going to go ahead and call that the normal direction. I'll just go ahead and put a unit vector on that to make it a direction. And then this is tangent to the surface, so I'm going to call that the tangential direction. Remember, if there is no frictional force between these, then there is no force component here at this interaction point in the tangential direction. If I wanted to, and again I'm not going to do this for this video, I'm going to later on in the video talk about how to write equations for the system. But if I wanted to, I could take this animal individually, find its momentum component in this direction, again in the tangential direction, and that momentum component would be constant because there's no impulse in this direction. And I could actually write a conservation of momentum equation. I would need this angle, and over here the tangential direction is something like this, and I'd need this angle. And in fact, I'll go ahead and do this. Let's say that this were an angle alpha, and over here, here's an angle beta. Then that momentum equation would look like mb/vb1 cosine alpha. That would give me the component of this animal's momentum in this direction. And that would equal the component of this momentum vector in this direction. That would be mb/vb2 cosine beta. This equation can be written because there's no, when we look at this picture, these normals, specifically this one, does not have a component in the tangential direction, and therefore that momentum component is constant. All right, what else could we possibly do? Let's see how many of these I can get rid of. All right, again, focusing on this guy. If this were my system, and I knew the angle between VA1 and the tangential direction, which is this angle, I could equate this guy's tangential momentum component to this guy's tangential momentum component, right? So it is possible to write equations for individual masses during this impact if the direction is chosen very carefully. Now, you can also write equations, believe it or not, for the normal direction. However, that involves a concept called coefficient of restitution. The purpose of this video is not to get into that, so I'm just going to skip that for now. If you're interested in coefficient of restitution and how to write an equation in the normal direction for an individual mass, see my it'll probably be video 2 or video 3 on this series on oblique impacts. But I'm gonna save that for another video. So again, individually, these masses, you can write a momentum conservation if you're very careful about the direction that you apply it in. And in order to decide the direction, you have to look at the normal direction, and then you'd apply it in a direction perpendicular to that. Right. Now, in this video, I'm going to focus more on how to write equations for the system. If we define our system as the pair, then these normal forces or these normal impulses are internal to the system. Therefore, the net impulse is 0 and momentum is conserved for the system. That allows you to write a momentum conservation in any direction you feel like. You can just pick a direction, write an equation. So I'm going to go ahead now and put in a set of coordinates here, and I'm just going to do a standard XY coordinate system. So I'm going to put in another coordinate system here. Let's see, and I got to choose a color for that. I'm going to use this purple here. All right. So I'm going to go ahead and put in a coordinate system now that looks like this. And you don't have to put your coordinate system here in the center. You can put your coordinate system anywhere you want in the picture. Oops. All right, darn it, got to get rid of that. Okay, so I'm just going to call that the x direction now, or we could call that the I direction. And then this one's going to be the y direction. So this is a standard xy coordinate system. So I realize in the center of my picture I have a lot going on. Again, the important thing to realize, in black these are forces. In blue these are directions. These are just coordinate directions. This one tangential, this one normal. And then in purple, or I guess pinkish here, kind of a standard xy coordinate system. If I wanted to, now that I've made a decision that the net force is 0, I actually could just delete this entire central picture here, because it's really no longer relevant to the discussion for the system. Again, because the net impulse is 0, I can write a momentum equation in any direction I want. So I'm going to use this standard xy coordinate system. Now, in order to do that, we would have to know some geometric angles here. So I'm going to go ahead and give this angle a name here. I guess I'll call that alpha. That's going to be the angle between VA1 and the x direction. And I'm going to come over here and call this angle beta. Over here we're going to need angles. Let's see, how about, I think that one is the Greek letter gamma. And then over here, I'm running out of Greek letters here, that's the Greek letter phi. It doesn't really matter what we call all these angles. We could call these like little a, little b, little c, little d or something. It's pretty standard in math and in physics and engineering to use Greek letters for angles. Now that we have these angles, let's talk about all the different equations we can write. First, conservation of momentum in the x direction, right? What might that look like? So I look at my picture here, picture 1 before impact. This animal here can be broken into components that look like this and this. This component is adjacent to alpha. Therefore, it's going to equal, well, technically this would be VA1 cosine alpha. Therefore, the momentum is going to be MA VA1 cosine alpha. Now, in my picture, these are velocity vectors, and I'm just going to leave them as velocity vectors. There's nothing wrong at all with just putting an m in front of each one of these and calling them momentum vectors. The only difference between a velocity and a momentum is that factor of mass. I'm just going to leave these as velocity vectors throughout the picture, but when you write your equation, these have to be momentums. Okay? This guy's x momentum, again, if I draw this guy's components, whoops, and I like to draw components in red. This guy's x component would point this way, y component this way. The x component is adjacent to beta. So this is going to be plus MBVB1 cosine beta. So this product represents the net momentum of this system in the x direction. Okay. I think I'm going to need a little more room than I have, so I'm going to take this, whoops, move it over to the right here. Okay, now, net momentum in the y direction. So this guy has a momentum component y direction of MAVA2, so that would be the hypotenuse of the momentum vector, multiplied by cosine of gamma there gives me the x component. Right, this vector right here needs to be multiplied by cosine phi to give the x component. So that thing's momentum component, x direction, is going to be mass b, VB2 cosine phi. Getting a little hard to read. VB2, and I'll just shorthand that, cosine phi, cosine of this angle right here. These are all positive because all of these momentum vectors or components in this picture point to the right. The equality is because of this picture. Again, whether when you're talking about whether a momentum is equal, it's all about the impulse picture. Because of how we're defining our system, the net impulse is 0 because this force vector added this force vector is a 0. Or again, in physics, we would say that that's an internal force to the system. And that's why we can put that there. All right, another equation we can write for the system. Conservation of momentum in the y direction. And I'm going to go ahead and call up positive for this. And although I didn't, I should have. When you write out an equation like this, conservation of momentum x direction, momentum's a vector concept. So you should always indicate what direction you are calling positive. When I wrote this equation, I was doing right positive. When I write the next equation, I'll go ahead and do up positive. And these are completely arbitrary. If you want to do down positive, it's perfectly fine. So, looking at this initial vector here, take note that this guy's velocity component in the y direction is down. So the first momentum term is going to be minus MAVA1 sine alpha. Sine because that's going to pick off the y component of this guy's momentum. Minus because that component points down. All right, we'll talk about mass B here. Taking note that this guy's velocity component is up. So the next term is going to be plus MBVB1 sine beta. Right. Over on the right, going back to mass A here. Okay, VA2 has a positive y component. That would be opposite the angle I called gamma. So the next term is going to be MA VA2 sine gamma, whatever that is. And again, positive because this thing's y component points up. Taking a look at mass B here, the y component of this velocity vector points down. So the next term is going to be minus MBVB2 sine phi. And again, the equality can be put here because the net force on the system during impact is 0. Now, this system of equations would be good for solving for up to 2 unknowns. This is a 2-dimensional problem, and we got a pair of equations here. Then the million-dollar question is, what if we have 3 unknowns? Well, there's a couple possibilities. The first one, which I talked about earlier, is about what's called the coefficient of restitution, which allows you to write equations for each of these individually in the normal direction, but I'm going to save that for another video. As far as the system and how it's defined, we could get a third equation if energy is conserved. So again, in some impacts energy is conserved, and in some impacts it's not. It typically depends on how hard the materials are. When materials, anytime you have an impact and there's a permanent deforming of material, kinetic energy will not be conserved. But in cases like pool balls hitting one another, where there's very, very little deforming material, that's pretty close to a conserved energy case. I say pretty close, it's not perfect. The fact that you can hear pool balls collide means there had to be some energy loss, but that's going to be very, 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 very little. So where appropriate, you can sometimes write a conservation of energy equation, and I'm going to have to get myself a little more room to do so. So I'm going to take this whole deal and maybe shrink it down a little bit and move it up a little bit. All right, so then, if appropriate, I'll put if possible here. Actually, possible is not the right word here. If, what's the word I want to put here? Yeah, appropriate's the best, sorry. So, if appropriate, we're going to write a conservation of energy equation. And again, the appropriate would be if the material's really, really hard, like pool balls or steel bearings, or molecular impacts. This is really good, like when 2 protons collide, that's pretty close to an energy conserved case. Then we can equate the kinetic energy here to the kinetic energy here. So the kinetic energy in picture 1 is going to equal 1/2 mass A times VA1 squared. All right, this guy's kinetic energy is 1/2 mass B times VB1 squared. So this sum represents the total kinetic energy in picture 1. All right, taking a look at picture 2, the total kinetic energy would be 1/2 mass A times VA2 squared plus 1/2 mass B times VB2 squared. So this represents the total kinetic energy in picture 2. And again, if appropriate, we can put equal sign. And again, the appropriateness depends on the nature of the impact. If you're familiar with the concept of coefficient of restitution, I believe a coefficient of restitution of, I can't remember if it's 1 or 0, I think it's 1, is a energy conserved impact. So again, I think whether this equal sign goes here, it's really about the materials in contact, and typically it's a judgment call. It's whether or not there's permanent deforming of material. So again, a couple of steel bearings hitting one another, it's appropriate to maybe say this is equal, or at least approximately equal. Or pool balls are another good example, or electron-electron impacts, or proton-proton impacts. In the case where cars collide at relatively high speed, where there's a lot of damage, no way would we put an equal sign. The appropriate thing to put here is this, that the initial kinetic energy of a system is less than or equal to, whoops, I got that the wrong way. The initial kinetic energy of the system is always greater than or equal to the final kinetic energy. The equality only shows up depending on the materials. So again, the point of this video is how to write, what type of equations to write, and how to write them when defining a system as a pair of particles for an oblique impact. Typically that'll allow us to write 2 momentum equations and possibly 1 kinetic energy equation to solve for up to 3 unknowns. I hope this video helps demonstrate these concepts. Have a great day.